Imagine you're a pilot flying a stealth fighter or a soldier deep in hostile territory. Your life and the mission depends on knowing exactly where you are. You glance at your display, and then nothing. The signal is gone. Or worse, it's lying to you. Your instruments say you're over the target, but you're actually drifting miles off course, straight into an enemy ambush. We live in the age of GPS. Since 1995, the global positioning system has become the invisible backbone of the entire world. It guides our missiles, tracks our supply chains, and tells your Uber driver where to pick you up. Modern warfare and modern society is addicted to the assumption that we can always see the sky, and the sky can always see us. But here's the terrifying truth. That assumption is wrong. The Department of Defense knows it. Military strategists are losing sleep over it. GPS is fragile. It is vulnerable. And in the wars of tomorrow, it will likely be the first thing to die. So, how do you navigate a battlefield when the satellites go dark? How do you find your way in a world without GPS? Today, we are diving into a comprehensive analysis of the future of navigation. We're talking about quantum compasses, magnetic maps, and autonomous swarms that build their own reality. This is the race to reinvent how we find our place in the world. To understand the solution, we first have to understand the problem. Why is GPS, this technological marvel, actually a massive strategic weakness? It comes down to physics. GPS satellites orbit about 20,000 kilometers above the Earth. By the time their signal reaches you, it is incredibly weak. Think of it like this. A GPS signal is like trying to spot a 25-watt car headlight from 12,000 miles away. The power of that signal at the Earth's surface is roughly 1 × 10 to the minus 16 watts. That is a staggeringly small number. Because the signal is so quiet, it is incredibly easy to shout over it. This is called jamming. A cheap, store-bought jammer with the power of a light bulb can drown out GPS signals for kilometers. But jamming is just brute force. The scarier threat is spoofing. Spoofing is when an adversary sends out a fake GPS signal that looks real but carries the wrong data. It's not jamming your radio. It's gaslighting your computer. We've already seen this in the real world. Ships in the Black Sea reporting their position as being at an airport miles inland. And then there are the environments where GPS just physically doesn't work. We call these GPS-denied environments. Deep urban canyons with tall skyscrapers, inside concrete bunkers, or subterranean tunnel networks. If a war moves underground, satellites are useless. Military doctrine has recognized that reliance on GPS is a single point of failure. So, the race is on for PNT, positioning, navigation, and timing. That works when the lights go out. Let's look at the first and most sci-fi solution, quantum navigation. If you can't look up at the stars or satellites to find your way, you have to look in. You have to feel how you are moving. We've done this for decades with inertial navigation systems, or INS. These use gyroscopes and accelerometers to track movement. The problem is mechanical sensors drift. Over time, small errors add up. After an hour without GPS, a standard fighter jet might be miles off course. Enter quantum navigation. This technology uses the weird laws of quantum mechanics to create a compass that basically never drifts. It relies on something called cold atom interferometry. Here's the simple version. Scientists use lasers to cool atoms, usually rubidium or cesium, down to near absolute zero. At that temperature, atoms stop acting like billiard balls and start acting like waves. When the platform moves, a tank, a submarine, a plane, that movement changes the phase of the wave. By measuring that change, we can calculate acceleration and rotation with mind-blowing precision. How precise? We're talking about a system that could operate for days or even weeks without a single GPS update and still be accurate within meters. And the best part? It's completely self-contained. You can't jam it. You can't spoof it. It's a black box sitting in the hull of a ship, measuring the universe at an atomic level. Now, there are challenges. Currently, these systems are large, power-hungry, and sensitive to vibration. Not exactly something you can strap to a soldier's helmet yet. But the tech is shrinking fast. We are looking at a future where vehicles and aircraft carry unjammable quantum compasses. While quantum physicists are working on the future, other engineers are looking to the past. Sometimes, the old ways are the best ways. They just need a digital upgrade. Before GPS, we had radio towers. One of the leading alternatives today is ELORN. Instead of satellites in space, ELORN uses huge transmitters on the ground, sending out low-frequency radio waves. Why is this better? Signal strength. Remember how weak GPS is? ELORN signals are millions of times more powerful. They are incredibly hard to jam. Plus, the low frequency allows the signal to penetrate buildings and even go a little bit underwater. Nations like the UK, Russia, and China are already building these networks as a backup shield. But what if you don't have radio towers? Well, look up. We are seeing a resurgence of celestial navigation. Yes, sailing by the stars. But we aren't using sextants and paper maps anymore. Modern systems use high-speed digital cameras and automated star tracking algorithms. They can spot stars even during the day or through breaks in the clouds. They lock onto the constellations and calculate position instantly. It's passive, unjammable, and works anywhere on Earth, as long as you have a patch of sky. And then there's the method that looks down. The Earth itself has a fingerprint. The Earth's crust has magnetic anomalies, variations in the magnetic field caused by iron deposits and geological structures. These variations are constant and unique to specific locations. By using sensitive magnetometers, some of which use that quantum tech we talked about earlier, a vehicle can sense the magnetic field as it moves. It compares that reading to a stored map, like matching a fingerprint to a database. This is huge for submarines and underground operations where absolutely no radio signals can reach. You are literally navigating by feeling the magnetic texture of the planet. So far, we've talked about replacing satellites with atoms, stars, and magnetic fields. But what if you're a drone flying into a collapsing building, or a robot exploring a cave? You don't just need to know where you are, you need to know what the world looks like. This brings us to SLAM. Simultaneous localization and mapping. If you've ever seen a self-driving car or a high-end robot vacuum, you've seen this. It uses LiDAR, shooting millions of laser pulses per second, to build a 3D map of the environment in real time. It solves a paradox. To know where you are, you need a map. But to build a map, you need to know where you are. SLAM uses complex algorithms to do both at the same time. In a military context, this is game-changing. A drone flies into a GPS-denied tunnel. It scans the walls. It knows it has moved 10 meters forward because it can see the walls moving backward. It builds the map and positions itself inside it, all without a single signal from space. But it gets crazier when you add the swarm. Imagine dropping 100 tiny sensors or drones into a contested area. They talk to each other. This is called collaborative navigation. Maybe one drone catches a glimpse of a star. Another one reads a magnetic anomaly. A third one sees a landmark. They share this data instantly. They form a mesh network, a living grid of positioning data. If one drone gets jammed or destroyed, the network heals itself. They effectively create their own GPS bubble over the battlefield. This is the power of distributed intelligence. So, which of these technologies is the winner? Is it quantum, star trackers, magnetic maps? The answer is yes, all of them. The future of navigation isn't about finding one silver bullet to replace GPS. It's about fusion. We are moving toward multi-modal systems. A future tank or aircraft will have a central brain, powered by artificial intelligence, that listens to everything at once. It will use GPS when it's safe. If that gets jammed, it instantly switches to the quantum inertial sensor. It corrects drift using a star tracker. It navigates the street using LiDAR. The AI acts as the conductor, weighing the reliability of every sensor in real time. If the GPS signal starts looking suspicious, like that spoofing attack we mentioned earlier, the AI cross-references it with the inertial data. realizes the math doesn't add up, and cuts the GPS feed before it can mislead the crew. This provides redundancy. It provides resilience. It turns navigation from a fragile single point of failure into an unbreakable web of data. The era of taking being found for granted is over. For 30 years, we have lived in a world where a blue dot on a screen could instantly tell us our place on Earth. We built our armies and our economies on that blue dot. But as electronic warfare capabilities proliferate, the military is preparing for the lights to go out. The technologies we discussed today, quantum sensing, AI-driven mapping, terrestrial grids, are not just backups. They are the next evolution of how humans relate to their environment. And just like GPS started as a military project and ended up in your pocket, these technologies will eventually trickle down to us. Better self-driving cars that don't need satellites. Indoor navigation for rescue workers. Unjammable logistics for the global economy. The future of navigation is precise, it is autonomous, and it is completely independent of the sky. What do you think? Would you trust a quantum compass over a satellite? Let me know in the comments below. If you enjoyed this deep dive into the future of tech, make sure to hit that subscribe button and ring the bell so you don't lose your way back to this channel. Thanks for watching. I'll see you in the next one.